Okay, so just as a recap from the previous video, we discussed kind of in detail the mobile phase and what the mobile phase is and what the purpose of the mobile phase in regards to the compound. Why is it there? What does it do? What's its really purpose on how it pushes things through the stationary phase itself? So this is a picture of a traditional mobile phase jug. These jugs typically sit near the instrument or up on top of the instrument, and we've got pictures that will eventually show you of what this instrument does and what it looks like. But this is just a beaker or a 4-liter jug of mobile phase, and on the front you can kind of see it says water and a 0.1% formic acid solution. So we told you that many times it's methanol, water, acetonitrile, and maybe a buffer if it's anything else. But depending on what you're really separating, we can see weird solvents to come into the picture, like maybe formic acid, which is the reason that ant bites hurt, because they are injecting you with formic acid from their little mouth. But formic acid is one of those mobile phases that we can use through a separation process if needed. Mixes are very common, we said. So 60-40 mixes, 50-50 mixes, 75-25 mixes, 95-5 mixes. As long as it adds up to 100%, that's what you're after. So we can play around with the compositions of them. And we also said never let the column go dry. That is why that depressed man was sitting on the stool in front of his column. He always had to keep adding mobile phase to the column. So we often call this thirst. Never let the instrument go thirsty, right? These things are very thirsty. You constantly want to give it something to drink, and you never want your mobile phase to go dry. So that means if I've got this jug near my instrument and my instrument is pumping this mobile phase and using it to separate something, I keep an eye on the jug. 4 liters will do me for a very long time. But if it gets low, I want to make sure that I'm filling it, because that's very important. You never let it go dry at all. So this led us up to the story with the stationary phase. And we said there's 2 different types of stationary phase. Alumina was one of them, and silica was another. So here is the picture of silica. SiO2. And you know, silica is going to make a network, a cage in a way. And silica, if you look down here at the very bottom, here's your SiO2, right? And this silica is going to start pairing up with other silica compounds. SiO2 networks is what we call that. And then the end of one of these oxygens that's exposed to the surface, that's on the outside of this piece of maybe lattice, if you want to think of it that way, is an OH group, just to satisfy the oxygen. And that OH group is what we would call an alcohol group, and that group is very polar, and the oxygens are polar, and silica as a whole is polar. So this is a very polar stationary phase that we have. So there's one of the examples of the stationary phase on the inside of a column. Now that's just silica. If it's just silica only, that is what it looks like. Silica you run across every day, whether you realized it or not. Anytime that maybe you buy a piece of food or a piece of clothing or a piece of electronics, if it has to stay dry and the moisture stays out of it, they typically put these small little packets of what they call silica gel on the inside. And you know as well as I know, it's not really gel, is it? These are hard little beads. Well, they call it gel because of its makeup. It is somewhat porous, and because of that, it's kind of jelly-like, not jelly as in Jello, jello, but it is porous. It's kind of like a sponge. So the silica gel is very common, and this is exactly what we use in the columns when we need it. The only difference is that we don't have beads of it like this. They, in the manufacturing process, will take these beads and they crush them down into a very fine powder. And when they crush it down to a very fine powder, they bottle it up and they sell it to us in form of silica. And we take this very fine powder and then put it into a column if we have to make a column by hand. So that's what the OH groups are called. They're alcohol groups. It is a polar substance, and desiccant basically means that it dries out moisture. It absorbs the water from the atmosphere so things do not start to sweat and things do not start to get wet. This is the structure for alumina, Al2O3. Slightly different than silica, right? We look at Al2O3 there. It's not like silica, it's a little bit different. And alumina has a different polarity as well. So there's a different attraction to these compounds. So things will separate differently in silica than they would in alumina. The order might be the same. The amount of time that they spend in the column might be a little bit different. But there's different attractions because they're different compounds, and we get different types of separation because of that. Both silica and alumina look very similar. You know, here's a picture of alumina that we use in the laboratory, and this white powder goes inside of the column if we have to hand make one. That's what happens. All right, so there's our two stationary phases. So if I go back and just jot down the note again, my stationary phase is going to consist of silica or alumina. All right. The problem. The problem with this technique is that if I use silica or alumina, these things are polar. And HPLC has found its home in a couple of different types of industries. One of these industries is pharmaceuticals. Pharmaceutical companies love HPLC every single day. The samples that they run extremely well on the instrument. It's suited for the instrument, and they're very clean, and the prep work is very small for the most part. So pharma loves it. Environmental loves it. Environmental looks for things like pesticides and herbicides, and we're going to put food into the environmental category as well, food and beverage. So food and beverage companies, environmental companies, if they're looking for pesticides and herbicides, HPLC does a very good job separating those components under the right circumstances. The problem is that pharmaceuticals, herbicides, pesticides, any of these other compounds that typically behave very well on the instrument, all of these things are nonpolar in nature. So we can't really do polar and nonpolar combo that way, right? If I take these compounds and make a column that has silica as the stationary phase, these are wasp and these are flowers. So if I dump these types of compounds into the column, the wasp will fly straight through. These compounds will go straight through. So we're going to have to modify something here. We don't want these compounds to fly through the column. There's no purpose in that. If we have to separate these compounds up here in whatever industry that we're working in, putting them in a tunnel where they have no attraction is not going to do us any good. Okay, so SiO2 and alumina, they're not going to cut it for me. They're kind of bad. So I need to modify them. I need to modify the silica, and I need to modify the alumina. And I need to put a non-polar part on the stationary phases. So that way these non-polar compounds can react and attract themselves to the non-polar stationary phase. Okay, so here's a silica particle. Let's just say that silica, that's the compound of silica. We'll just call it a particle. It's easier to draw this way and maybe to understand. And as it is, silica is very polar. No attraction there to medicines or pesticides. Maybe caffeine from my chocolates or my coffees. No attraction. It's not going to do well at all. So I modify the surface is what I do. And I add little fingers and hands and arms onto the silica or to the alumina. And these little fingers and these little arms are what will reach out and grab a hold of these compounds as they travel through the column. But these little arms and fingers have to be attracted to the non-polar compounds. Therefore, these hands and fingers are made up of two substances. One common choice is what we call a C8, and the other common choice is what we call a C18. And C8 and C18 is what you would expect. C is going to stand for carbon. So this is 1, 2, 3, 4, 5, 6, 7, and 8. An 8 carbon chain that gets loaded on the silica or the alumina surface. We've got to have a foundation to start with. Silica and alumina is our foundation. Companies make modified silica and alumina through a series of reactions where they can put C8 onto these particles or C18. And if you really want me to do it, I'll do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So these are the two modifiers. Not the only two, but two modifiers that we use to modify the surface of the alumina and the silica particle. So now what we've done is that we've taken alumina and silica as our foundation. We've modified that particle to put an 8 carbon chain or maybe an 18 carbon chain onto the surface of the particle itself. And now this is becoming more non-polar because of all of those carbon chains. Nothing special about them. There's no free pairs of electrons on C8s or C18s. It's all carbons and hydrogens, right? All the way through. So now these nonpolar molecules can go through the column and they can see these big long fingers of an 8 carbon chain or an 18 carbon chain that's reaching out for them. And these carbon chains are reaching out for them and they grab a hold of the particles as they come through and they hold on to those particles momentarily. And they lag it behind. Almost like a mosh pit in a way. All of these hands are reaching up for you to take a crowd dive, right? And then when you do that, these fingers and the hands, they just kind of take you, which is the compound, and they move you through the pit. And you just kind of go along for the ride. Whatever direction the pit decides to take you, that's the direction that you have to go into. And that's what's happening on the inside of this column. It is a fancy mosh pit with your lead singer being the component of interest. So in the next video, we'll take a look more specifically at the stationary phase, look more closely at the C8 and C18, and describe the process that's happening through those carbon chains and carbon fingers.